The first lesson in the chemical bonding and nomenclature unit is on the octet rule and ion formation. In this video, we will have a few learning targets. We're going to do the first two here together. We want to be able to state the octet rule and apply it to ion formation, and also to differentiate between cation and anion formation. The octet rule says that atoms are most stable with a full outer energy level. Now, if that outer energy level is the first energy level, then that energy level would be full with 2 valence electrons. If the outer energy level is any other energy level, then we're talking about 8 valence electrons. Thus, it's called the octet rule, referring to the number 8. Atoms will either gain, lose, or share their valence electrons to achieve this octet. Now, for a great majority of this unit, we will be simply focusing on the gaining and losing of the electrons. The sharing will come towards the end. Some definitions we want to be familiar with. An ion is simply a charged atom or group of atoms. A cation is the name that we give to a positively charged ion, while an anion is what we call a negative ion. The focus of this video will be on monatomic ions, and those would be ions that are made of one atom. Notice the prefix mono in front of the word atomic there, prefix mono meaning one or singular. Let's consider how cations are formed. Metals will lose valence electrons to form cations, and let's examine why that is. Let's start by looking at the group 1 ions. All group 1 ions are going to have a 1+ charge to them, and you'll see why here after this lesson. Let's consider the element lithium. Now, if you look at your periodic table, you'll see lithium is atomic number 3, so it would have 3 protons. And then if it's a neutral atom, it would have 3 electrons, with one of those electrons being a valence electron in the second energy level. We know it has 1 valence electron because it's in group number 1. Here's a diagram of a lithium atom. We have the nucleus here in the middle shaded in gray, so there'd be 3 protons there. And notice we have 2 energy levels, and these black dots represent electrons. Notice there are 2 electrons in the first energy level, and there's 1 electron in the second energy level. Well, when lithium is going to form an ion, it's either going to gain or lose electrons, and it's going to do so to make its outer energy level full. So there are 2 options. Lithium could either gain 7 electrons, and those would all go in this second energy level. Consider this. If it gained those 7, it would then have 8 valence electrons. Well, that would fill its outer energy level and make it most stable. However, there's another option. It could also lose electrons. If the atom is going to lose electrons, it would only need to lose 1. It would only need to lose this singular valence electron. The reason why that is now the previous energy level, in other words, the first energy level, would be the outer energy level, and notice it has 2 electrons. The first energy level is full with 2 electrons. So that's what happens. The lithium is going to lose the 1 valence electron, and then notice what we have here. We still have the nucleus, which would still have 3 protons in it, because nothing happened to those. We then have the 2 electrons in the first energy level, and now that second energy level is empty, because it lost its valence electron. So we lose the 1 valence electron. Well, what that leads to then is we have an atom with 3 protons and only 2 electrons. There's 1 more proton than electron. So now we have an ion. We've gone from a neutral lithium atom, where we have the same number of protons as electrons. We lose an electron, and now we have a lithium ion. And notice the notation here. We can write that one of 2 ways. We use the symbol for lithium, Li, and then as a superscript on the right side, we can either put 1+ or plus, either one. If the coefficient out front is not there, then it's understood to be 1. Let's look at a different atom in group number 1. Let's take a look at sodium. Sodium is atomic number 11, so it has 11 protons. If it's a neutral atom, it would have 11 electrons. Because it's in group 1, we know it has 1 valence electron, and that would be in the third energy level because it's in the third period. So here's a diagram of a sodium atom. Notice we have 3 energy levels. The first energy level just has 2 electrons in it. The second has 8, and then the third energy level just has the 1. So the 1 valence electron for a total of 11. Well, we're presented with the exact same options here as we were with the lithium. It could either gain 7 electrons to reach its octet or lose the 1. Well, it would be much easier for it to lose the 1 than it would be to gain 7, so that's what happens. The sodium atom loses the 1 valence electron, or the outer electron, and notice what we're left with. Our outer energy level is now the second energy level with 8 electrons, so it's full, it's most stable. So just like the lithium, the sodium will lose the 1 valence electron. That would give us 1 more proton than electron. We'd have 8 of those valence electrons in the second energy level. So just like the lithium, the sodium has a 1 plus charge to it because it lost 1 electron. Now if you consider this, we could draw a similar diagram for each of these elements in group 1, and they'd all be the same thing. All these group 1 elements would all form a 1 plus charge. So on your periodic table, what you want to do is somehow indicate that group 1 ions are always going to be 1 plus, because they'll always lose their 1 valence electron. Let's take a look at group 2 now. And as we'll see in this discussion, all of these metals will form a 2 plus charge. Let's consider magnesium. If you look at magnesium on the periodic table, you will see that it has 12 protons because it's atomic number 12. Thus, if it's neutral, it would have 12 electrons. And then, because it's in group 2, it has the 2 valence electrons. So here's a picture of what might happen when magnesium forms an ion. Here's our neutral magnesium atom. Notice we have 2 valence electrons in the outermost energy level there. If it loses those 2, what we're left with are just 2 energy levels, the outer of which has the 8 electrons in it, so it meets the octet rule. And because it's lost the 2 electrons, it now has a 2 plus charge. If you're not sure where that comes from, consider this. It still has 12 protons, but because it lost 2 electrons, it now only has 10 electrons. Thus, there are 2 more protons than electrons, and we get a 2 plus charge. So we've gone from a neutral magnesium atom to a magnesium ion, which is 2 plus. Just like we said with the group 1 elements, we could go through this same thinking for all the group 2 elements. So all group 2 ions all have a 2 plus charge to them. There are a few other metals that always form 1 monatomic cation. Aluminum is always 3 plus. Silver is always 1 plus. Zinc is always 2 plus. There are a few others actually, but these are the most common. That's why I mentioned them here. So somewhere on your periodic table, maybe directly in the box for each of those elements, you might want to mark this, that the aluminum ion is always 3 plus, silver is always 1 plus, zinc is always 2 plus. Most of the other metals, namely the transition metals, most of them will form multiple ions. And what we mean by that is this. Copper, for example, will form a 1 plus ion where it loses 1 valence electron. It will also form a 2 plus ion when it loses 2 electrons. Likewise, iron can form 2 plus or 3 plus. Now, these are not things that you need to memorize here. As we go throughout the unit, I'll show you how we can determine what the charge would be for a particular ion in a particular compound. But for now, we just want to understand that all these other metals, they are not limited to forming just 1 monatomic ion. Another example here, vanadium can actually form 4 different ions, as you can see here, 2 plus, 3 plus, 4 plus, or 5 plus. Now let's consider anions. Recall, anions are negatively charged ions. These are formed by nonmetals. Nonmetals will gain valence electrons to form their anions. Let's take a look at the halogens. Recall, halogens would be in group 17. These are going to be elements that form ions that have a 1 minus charge. Let's consider fluorine. Fluorine's atomic number 9, so it would have 9 protons and thus 9 electrons if it's neutral. Here's a diagram for a fluorine atom. Notice if we count up the electrons here, there's 2 electrons in the first energy level, and there are 7 in the second energy level. So the 7 valence electrons. To form an octet, fluorine would have 2 options. If it were going to lose electrons, it would have to lose all 7 valence electrons. Well, that's not very practical, considering the other option is to simply gain 1. If it gained 1 valence electron, it would then have a full outer energy level, because that would give it 8 valence electrons in that second level. So that's what happens. The fluorine is going to gain or receive 1 electron from somewhere, and then what we end up with then would be 8 electrons in that outer energy level, so we've met the octet. So we gain the 1 valence electron. That's going to take us up to 10 electrons compared to the 9 protons that the atom has. So that's going to give it a negative charge. And again, we would write that with a superscript on the right side. Notice the negative there. We can either write it as minus or 1 minus, either one. And then notice the name on it. This would be called the fluoride ion, not the fluorine ion. With the monatomic cations, the metals we just saw, the names don't change. So for example, we have the sodium ion or the lithium ion or the magnesium ion. With monatomic anions, we change the ending of the name to IDE. So it's not the fluorine ion, it is the fluoride ion. So we could have this same discussion with all of the halogens. So all those group 17 nonmetals, the charge on their ion will always be 1 minus. Now let's consider group 16 nonmetals. They're all going to be 2 minus. Let's take a look at the element oxygen. Oxygen has 8 protons, because it's atomic number 8, 8 electrons if it's a neutral atom. It's in group 16, so it would have 6 valence electrons. Here's a diagram for an oxygen atom. Notice it's 6 valence electrons here. So again, there would be 2 options for filling its octet. And it could either lose 6 valence electrons or it could gain 2. Well, the easier option would be to gain 2. So if it does that, it will now have a 2 minus charge, because now it has 2 more electrons than protons. So we've gone from a neutral oxygen atom to an oxide ion. Notice the IDE ending, and it has a 2 minus charge. And again, this would be true of all those group 16 nonmetals. They'd all have a 2 minus charge. Let's take a look at group 15. If you follow the trend here, you'll see these will all be 3 minus. If we look at nitrogen, nitrogen has 7 protons because it's atomic number 7, and it has 5 valence electrons. It's in group 15. So notice our diagram here, we have 5 valence electrons. It would then gain 3 to fill that octet. Notice the electrons here that are marked in blue are the electrons that have been gained. So we've gone from 7 electrons, now it has 10 in total because it gained 3. So that would give this ion a charge of 3 minus. So we've gone from a neutral nitrogen atom. Now we have a nitride ion. Again, notice the IDE ending with a 3 minus charge. A question to consider. Noble gases rarely form ions. Why not? Or why, I suppose we could ask. Go ahead and pause the video and ask yourself that question. I assume you've had a chance to think about this. If you consider noble gases, remember those are elements in group 18, and those already have a full outer energy level. They already have 8 valence electrons, or in the case of helium, it has the 2 valence electrons in the first level. Meaning for noble gases, their outer energy level is already full. So if a noble gas were to form an ion, it would have to gain or lose electrons just like any other atom would have to. But that would actually result in it becoming less stable, because it would be going from a full outer energy level to a non-full outer energy level, either by gaining or losing. So this is why noble gases would not form ions very often, although if you add enough energy to them, you could get it to happen. So we've taken a look at these first 2 learning targets here. We've stated the octet rule, and we've applied it to ion formation. We've also differentiated between cation and anion formation. What we should be able to do now is to predict the charge on monatomic ions. And I just have a series of questions to help you understand what we mean by that. So here's an example problem. For each element, we need to determine several things. A, the number of valence electrons. B, if the element will gain or lose electrons in ion formation and how many. C, the charge on its ion. D, the formula for the ion. And E, the name of the ion. So let's just take a look at these questions for a specific element. Let's answer these questions for phosphorus. So ask yourself, how many valence electrons does a phosphorus atom have? Well, if you take a look at the periodic table, it's in group 15, so it would have 5 valence electrons. Question B, if the element will gain or lose electrons in ion formation and how many? So phosphorus has 5 valence electrons. In order to form an ion, it would either gain electrons to get to its octet or lose electrons. Well, if it gained, it would have to gain 3 because it has 5 already. Gaining 3 would get it to 8. If it were going to lose, it would have to lose all 5. Well, the more likely option would be to gain the 3, so it would gain 3 electrons. If it gains 3 electrons, the charge on that ion would be 3 minus, so there's the answer to question C. Question D, the formula of the ion would be P 3 minus because it now has 3 more electrons than protons. And then the name of the ion, recall with monatomic anions, we use the IDE ending. So the name of the ion would be the phosphide ion. And here are all those answers. It has 5 valence electrons. It's going to gain 3 to get to its octet. The charge of the ion would be 3 minus. Here's the formula, P3 minus, and the name would be the phosphide ion. Let's answer those same questions for strontium. Strontium is in group 2, so it has 2 valence electrons. If it has 2 valence electrons, it would either gain 6 or lose 2. Well, the easier option would be to lose the 2 valence electrons. If it loses 2, it would have a charge of 2 plus because it would now have 2 more protons and electrons. The formula would be Sr2 plus, and then the name would simply be the strontium ion. Remember, with monatomic cations, we just use the name of the metal. So here are those answers. 2 valence electrons, loses 2 of the 2 valence electrons. There's the charge, the formula, and the name. All right, practice problem. Same thing, same question you just saw before. Please pause the video as each comes up and try to answer them on your own, and then resume the video and see how you did. First one here, we have iodine. I assume you've had a go of it. Here are the answers. Iodine has 7 valence electrons. We know that because it's in group number 17. So it'll gain 1 to fill its octet. Its charge would be 1 minus. The formula is I minus. This is the capital letter I here. At least it is in this particular font. And then the name would be the iodide ion. Again, the monatomic anions, we use the IDE ending. Sulfur. Sulfur has 6 valence electrons because it's in group 16. So it would gain 2 electrons. That would give it a charge of 2 minus. The formula S2 minus, and the name would be the sulfide ion. Rubidium. Rubidium has 2 valence electrons. It's in group 2. It would lose 2 of its electrons in to give it a 2 plus charge, and you can see the formula there. And then the name would be the rubidium ion. Alright, so in this video, we have stated the octet rule and applied it to ion formation. We've differentiated between cation and anion formation. And then lastly, we did look at the periodic table there to predict the charge on monatomic ions. In the next lesson, we'll be looking at how we go about using this idea to describe ionic bonding.